All right, let's start with today, storage and I/O, session 2. So last lecture we talked about the mass storage structure, the disk, magnetic disk, and tapes. Specifically, we covered a little bit of the performance metrics for disks. And also, we covered a few disk scheduling algorithms, first come, first serve, shortest seek time first. I think that's SSTF. Scan, C-scan, look, and C-look. Also, if you didn't check the Piazza, there's a post. Make sure you get the announcement and updates on Piazza. So the lecture is slightly updated. So just to, if you want to solve for homework 4, for example, C-look and C-scan, they were circular. They only service in one direction, and we just assume that's the direction from 0 to the track number 0 all the way up, and then they come back directly towards 0 again. Okay, not servicing anything. That will be the direction. Okay. So then I hope everyone did a good job on PA2. I haven't checked out the grades yet, but start immediately working on your PA3. The design document is going to be due this weekend. This Friday, and then also the homework 4. You are, I think, by this time, maybe after the session, maybe even before the session, you're basically done with whatever that you need for homework 4. So just make sure you solve it. And so today we're going to talk about a little bit on reliability of storage. And we're going to talk about what a transaction concept is. Usually, you might have heard that in a database, for example. And we're going to talk about the RAID systems, different levels of the RAID, and a little bit of an introduction into I/O. All right. So, reliability basically means that you don't lose your data, right? But it is necessary to know what's going on and what are the issues. So, for example, if your computer just loses power in the middle of an operation or a process, there are some things that are going to finish because there are basically specifications for power. So, for example, for ATX power, there is a power good signal that when you turn your computer on, there are a lot of ripples and noise in the power. Once it stabilizes, then it will let the motherboard know that, hey, the power is good enough, I think after 100 milliseconds after stabilization. And then the motherboard can start the CPU and everything else, right? Also, at the case of a power loss, when the power rails are, because the power is not an actual step that shuts down, right? Your power supply keeps its power, and it starts losing power gradually, and it might be fast, might be less than a second, maybe 100 millisecond or something, but still that's more than enough, right? Because if you have, let's say, 1 millisecond with the clock speed and everything, that quickly can generate an interrupt, and then that can run thousands of instructions on a CPU. Okay, so that's a lot of time, especially in if you don't consider any hard disk that takes a long time, for seek time or storage. There are a lot of things that you can do in that time. So the power, again, when it starts losing its power, once the power is out, it will basically interrupt the computer that, hey, the power is out. I'm just going to keep you alive for, 10 milliseconds. I don't know, somewhere between 1 or 16 milliseconds. So do whatever you want to do. And then that's a non-maskable interrupt. The CPU quickly wraps up or does whatever it needs to do in order to save the states. Yes?
Now, for example, if this is losing power, right? But what happens if the switcher were to go to sleep, so it resumes back?
Those are all soft things. If you lose power in the sleep, to be honest, I'm not sure if they do something. During the sleep, usually. When you put the computer to sleep, it's not actually off. It just preserves the memory. The CPU even, I think it's in a low state power, but the boot up time is much more quicker, relatively, and the motherboard itself is on. It monitors everything. That's how basically it can tell that you press the key to resume, right? So during normal operation of coming back from sleep, it just it knows what to do, basically. It just realizes that it needs to wake up. It puts the CPU back into different power mode. I don't know exactly what are the the interrupts for the sleep. If you lose your power during the sleep, again, because the motherboard still knows what is going on, it can do. But I don't know exactly what are the instructions that will happen during that non-maskable interrupt. But yeah.
I believe it doesn't go to sleep right away. Like it saves it before it goes to sleep.
There are things that there are definitely things that it will save. It just doesn't shuts off like that. It doesn't doze off like that. Yeah, it definitely saves some states so that if in case of failure or something, it can at least recover up to some point. Okay. There are also basically hybrid sleeps, if you want to know. Hybrid sleeps are actually kind of combining hibernation and sleep. So what that is when you put your computer to sleep, it actually also saves the memory into the hard disk as a hibernate state, but it actually doesn't turn off. So on a normal case, it's just like sleep. Once you click, it just like wakes up. But in case of a failure, because it already has saved all the memory state to the disk, it acts as a hibernation. So you turn it on, it just loads everything and it doesn't lose, right? But it just takes a little bit longer to save your memory to the hard disk. All right. So, but again, you can't do everything that you want to do if you're running a simulation. Obviously that's not going to be not a priority for the system. So that's going to be interrupted and you lose data, right? And also, even whenever you are writing something on the disk, you remember the disk has a minimum amount of, the minimum transfer unit, which is like, for example, sectors. If you want to write a sector to the disk, then obviously maybe you don't want to replace the whole sector. Maybe you want to replace only a few bytes. How that works is that sector is going to be read, and then in the memory you're going to be modify those bytes, and then you're going to replace that sector. Now, in the middle of this replacement, even the data that you didn't intend to modify are basically getting replaced and then can be corrupted. Okay? So, this is not what you want. Basically, you want to be able to retrieve the data that you lose during some of these issues, right? And you used to probably have some of these issues much more before when you were working with FAT file system, for example. Still, you might do the same thing with the flash drives. If your flash drives are using FAT system, you just plug them out, and then your data is kind of corrupted. All right, that usually doesn't happen, for example, in X4 or X3 or NTFS file system because they implement some of these recovery steps. All right, so there are also other issues regarding caching on storage. So caching, we already know what it is, but we haven't actually talked about the caching a lot, and we're actually not going to talk about because it's a whole story by itself, especially the different caches of the processor, different levels, and now what happens even now when you have multiple cores, that's going to be even worse because you have to maintain consistency and so on. But anyways, so caching is easy to understand for reading because you're not changing anything, you cache something in, and now you have it available, you can read it at a faster rate, and there's no problem with that, right? How about writing? When you want to write something, if you cache something that you want to write, then what will happen in case of a power loss? You actually didn't write it, you just cached it. And this is also again, for multiple accesses, this is an issue. If you cache some data and then someone writes to it and then the other one wants to read, should they read the previous data or the new data? How do you manage that? But anyways, for this writing, there are two methods that you might have heard. One is write through, and the other one is write back. So write through is when you decide that, okay, my data that I'm writing is important. I want it to be written as soon as possible. I want to make sure. So what you're going to do is ask the operating system to flush it, right? You might have heard the term flush, right? So that's basically making sure that the data that you ask the operating system to write is actually written. It's kind of like blocking, and you wait till it's finished. The operating system tells you that, hey, I am finished writing it. Go ahead to your next step. Write back is delaying the write. So you're just offloading this to the operating system and says, okay, I'm assuming that the power is not going to go down. So just, make sure you write this, and I'm going to just keep continuing whatever that I'm doing. In the meantime, the operating system finds its own chance based on the I/O scheduling, based on the, maybe caches, maybe the process just keeps updating, right? The operating system doesn't need to write everything. As long as they're updating the same file, they have the cache. So every now and often, whenever they get the chance, they, write to the storage. Okay? So this is, again, usually much better in terms of performance of the process. You don't have to block your process. But again, there is a slight chance that something like that happens. Okay? Any question? All right. So there are also things that happen whenever you want to have multiple updates to let's say a file, right? If you have a file that you want to basically do a few updates on it, it's not that there's a single update that might fail, but maybe these updates altogether will define like a state. So you want to move from one state to another state, but between these there are multiple steps, right? And between these steps, if the data gets corrupted, it's not that you didn't actually, move from state A to B, but actually it's maybe an unknown state, or you lose something even worse, right? So let's say, for example, an example is like this. When you want to move a file between two directories, we have already learned what's going to happen in the directory and inode structure. But you can think of it that you add a file to the new directory and then remove the file from old directory, right? Either it's this one or the reverse order. If it's a reverse order, then if you lose the power, for example, in the middle of these, what's going to happen is that you're just going to lose the file altogether. If you add it to the second directory and then remove it from the old one, then again, in the middle of these, now you have two versions of the file. Again, that's probably not what you wanted, right? Or whenever you want to create a file, right? You have the allocating the space on the disk. You have you got to have the header and the data. Then you basically write to the disk and then add the file to the new directory. In the middle of this, what's going to happen is that you allocate data, then some of the disk space is just wasted. If you have something like this, then maybe if you have written the header but not the data, then basically your data is, again, you think that your data is there, but it's not. It's just some garbage. And if you do, So even, with write-through scenario, there are multiple steps at lower level that happen even that operating system doesn't know, right? So this can even get worse. So a single a logical file operation can involve updates to multiple physical disk sectors itself, right? Or disk block. So up to even some points, the operating system can know. So whenever you're modifying a file, there are things that operating system handles, like inode, the data blocks and headers, whatever, the metadata, but also even at lower level, like the operating system finally asks something for a block. Now the disk controller itself might have a remapping of the bad sectors. So now it needs to switch back and forth between different sectors in order to satisfy that single request, right? And now that the operating system doesn't even know about this one, right? It asks for one operation, as simple as that, but in the middle of them, again, you might just lose some of it, right? So some of this also is because at physical level, everything happens one at a time, right? And so when you want to write or read from disk, you are eventually reading it one sector at a time. And this is also something that you might want to change. You might want to have concurrent accesses. Last session we actually had a small discussion here how we can improve this. So today we're going to talk about that. And again, the consistency is something that you also want to guarantee. So the order of things, if you want to change this file and change this file, this may be your order. Now, if this happens and then before the other happens, something fails, then your state is basically even invalid because the order is also not preserved. Okay? So, now we get to the concept of a transaction. So a transaction concept, again, you might have heard of it in the database, is when you have a group of operations and they are like one unit, right? So even there are like how many they are, as long as you can make them have the ACID or asset properties, then these are basically the properties associated with the transaction, right? So what are they? The first thing is atomic, meaning they are one unit. Either they're, at state A, or they state B. There's no middle. We actually had atomic operations or instructions when we were talking about synchronization, right? Again, the implementation was different, but the goal was to make those operations atomic, right? So, again, this is something that we are thinking about it logically. You might have different ways of implementing it at physical level, so that you have this atomicity. So the other one is consistency. Again, if you are changing A before B and then C, this is also something that you want to be reflected. If there are multiple transactions, the order should be consistent. The other one is isolation. Different transactions should not basically see the effect of each other. Each transaction should be kind of isolated from the other ones. And last one is durable, meaning whatever that you have committed or completed should stay completed, right? Even on a transaction of a bank transfer, you can think of this, right? When you transfer something, you don't want your account to be, lose money, and then maybe this money is just gone and not added to your friend's account. From moving this money from here to there, it should be atomic, meaning either it says, hey, I couldn't transfer, so here is your money back, you didn't lose any money, or it's over, it's right there. It should be consistent. So again, if you're just transferring a bunch of money here and there, everything stays the same, you don't end up in a state that you subtract some money that you didn't expect, or you subtract something from $100 you're giving to this friend, 200 to the other one, and then kind of get messed up. You don't want that. Isolation, if you have enough money in your account, obviously, then you don't want these to affect each other. If I'm transferring 100 here, 200 here, they don't need to basically conflict with each other. They don't need to necessarily see the effect of each other. Again, I'm assuming that you have enough balance. And durable. So once the transfer is done, no matter if the next transfer is completed or failed, whatever, that transfer should stay completed. You should not change anything that has already been done. Okay? That might be like PayPal scamming. Okay? So next we're going to go for implementation of transactions. So the idea is basically to have the disk, to be able to recover disk, right? So if you change some of the change, if you basically put all the changes that you want to do in a single write, then it will be kind of atomic, right? You either have it finished or not. You won't lose the state in the middle, right? So this example I think I already gone through. So something that you can do in the disk is that even though you might have a lot of operations on the disk, you can have a log on the disk that basically records what are the changes to be made to the disk, right? So this way, this itself is you do this first, and then in the middle of the operations, if something fails, you're basically going to check this log, right? You're going to take a look at this log and see, oh, I was supposed to do this and then do this and then change this sector and move this sector to here and everything. Did I get to finish it? Yes or no? If by the end of the operations, it will also be recorded. So then you'll know that it was finished. If it was not finished, then you can see in the log, oh, I started something, but I didn't finish it. So I lost power or had a crash or somewhere in between. So can I recover? Again, by redoing this log, replaying this log, you can basically repeat and it's maintaining your state. It's not you haven't actually changed anything from state A. It's a little bit difficult, I think, in terms of this example. Otherwise, you have to completely go through a detailed example. But let's see. Let's say I want to copy file A from here to file B over here, right? So if I log this, that I want to copy file A from here to here, then it will be, it will be recorded somewhere. Now I know what I'm going to do. Normal case, you make the copy and then you wrap up, you just clean it off or mark it as finished, and then everything is fine, right? Now, if your implementation of copy is somewhat repeatable, or you're not losing data, for example, in the case of you don't actually overwrite a file. If I want to copy A to B, I'm first going to write it into a temporary area, and then I'm going to rename it, right? So this way, when I do that, if in the middle of it there's a crash, then when I boot up again, I can take a look at the log. Oh, I was supposed to do something, but I didn't get to finish it, right? But because I didn't get to finish it, then I haven't lost anything because I didn't overwritten anything. It's as if I just didn't do anything. I know that I didn't remove a file in the process. So then I can go ahead and do that. So I can just repeat the log. Okay, I was supposed to do this. Now I'm going to finish it off. Okay. So this is basically something which is called like a journal. So X4, for example, does that. NTFS does that. There are a lot of extra steps to make it recoverable. That's why you probably have much less data corruptions in these file systems. And you might have seen that when the system boots up, for example, it checks its journal to see, whatever that it was supposed to do, or if the file system is, was in the middle of something, and then if it was, then it tries to, use that journal and then fix it. Okay. Again, this is just an idea. The details of NTFS and X4, we're not going to talk about it. I myself actually am very interested to know exactly what's going on, but just remember that that's something that needs extra operations in terms of read and write to the file. But again, this is done to ensure reliability of the system. Okay. All right. So we'll get to RAID. Any question before we starting RAID? So RAID is when you have multiple disks and you want to basically use them a little bit better to get more performance or reliability. That's the overall idea. Okay. So RAID stands for redundant array of inexpensive or independent disks. Why two? I think initially the reason was that they used RAID for one purpose. Now they're using it for another purpose, right? Initially, disks of lower sizes were cheaper than larger disks, and it was not. It's never linear, right? So when you have 1 terabyte of data, 2 terabyte hard disk is not always twice that, right? There's always a trend. Right now, I think the trend is maybe 2 terabytes or 4 terabytes. So if you divide your capacity by half, your price doesn't get divided by half, and there's always a sweet spot. So right now, if a terabyte hard drive is $50, let's say, you cannot have 1 gigabyte hard drive for 10 cents. You just can't have it, right? On the other hand, if let's say 10 terabyte is $200, 20 terabytes, which is twice that, is actually going to expend. You have to spend more than twice to get that, right? So there's always a trend there. So at some point the problem was the storage capacity. So in order to double the storage, people didn't want to spend more than twice the amount of one disk. So instead what they did was that they used inexpensive ones and kind of bundled them together to logically have a larger volume, right? So the same thing. If you have now 10 terabytes for a 20 terabytes, then you use RAID and it will be a little bit inexpensive in that case. But now the storage is actually is used for different. Right now the capacities are much larger, and you know, with all the distributed uses of disks and file systems and everything. So the problem is not that. Now the problem is redundancy. So now what you do is you use RAID usually for reliability, okay, or performance. So basically there are multiple standard levels of RAID from 0 to 6. We're going to go over them quickly. Usually either you are dealing with 0, 1, or 5 or 6. But 2, 3, 4 are not that used. But we're going to just cover them and see what they are. Okay. So again, the idea, just remember, connecting disks together so that you get something out of them separate from, you know, treating each separately as different partitions or different disks. So either you combine them into a like one logical higher volume, or like have redundancy, you know, writing more than once, or writing extra data to be able to recover from failure. So these are basically what you need to do. One is data striping, which is splitting basically data into different blocks, right? If instead of like writing one block of data or file into one disk at a time, you can stripe this into, break it into different disks, right? For different reasons. Again, we're going to cover all of them. The other one is mirroring or shadowing, which is duplicating your data onto multiple disks. The same data, instead of like, you know, breaking it, no, the same data, but instead of just like writing it once, you're writing it twice. Okay? And the other one is like block interleaved parity. So this is when you have like a parity, and then you interleave it between the blocks instead of like mirroring. Instead of like completely mirroring a file, you basically put some redundancy, you know, bytes or bits in between, and so you get some redundancy, but not as much as a full mirror, okay? And now we want to make it as useful as possible, so we're going to see what's happening, for example, between RAID and 3 and 4 and 5, okay? So the first RAID is RAID 0. So the RAID 0 is basically known as the disk striping, and that is that you have like two disks instead of one. And you just like, again, remember, you're logically not seeing this at all. This is happening like behind the curtains, and then you get what the, you know, benefit is. So in the RAID 0, the two disks will basically act as one, and then they stripe the data. So whatever data you give them, some of them, like, you know, some of the blocks goes to this one, some of the other ones goes to this one, right? At the same time, this happens without you noticing it, right? So what's the benefit of this? So the first thing is that you get the capacity of disk 1 plus disk 0 together. So if this is like 100 gigabytes and this is 100 gigabytes, now you have one disk of 200 gigabytes. And then also, you're striping the data, so you get performance, right? So it improves read and write performance by, you know, paralleling. So instead of like writing blocks one at a time on one disk, A1, A2, A3, A4, like that, you're able actually to pass on two blocks at a time, and the RAID system can in parallel write them together on these, right? And again, when you also want to read the same thing, especially like sequential data, that's the same thing happens, right? So it reads this and this together at the same time, this and this together at the same time, and so on. Now, obviously, this is like in theory, there are overheads, or for example, what if like you want only, for some reason, you want only odd blocks? Then, you know, you have to read this, and then this, and then this, right? There's still the worst case that, or for example, if you just want to read one sector, you still need one sector from one hard drive. So that's not going to improve, right? So, but overall, you know, performance is going to be better through that. But the problem is with RAID 0, it does not provide any fault tolerance. So if you have like if you have your data like split into two disks like that, what happens if this one just fails? You basically lose all your data. I mean, you lose half of your data, but then you lose all of your files that you wanted. Yes?
But if you had just one, you lose all of it.
Yes, but the chances of failing one of two disks is much more than I mean, it's more than if you have one disk and then failing that disk. Right? But again, yes, but the key idea here is that RAID 0 doesn't provide any fault tolerance, right? Because we talked about like RAID gives you either performance or reliability or both, but RAID 0 doesn't give any fault tolerance at all. Okay? So, on the other hand, RAID 1 do the opposite. It basically mirrors the whole disk. Whatever that you write into this is going to be written into this as well. So the idea is that in case that you fail one disk, you have a whole other disk that has everything that you have. You basically lose nothing, right? So it's like disk mirroring. Again, it's mirroring the whole disk, right? And so it provides a fault tolerance, and it improves the read performance. Right? Even though the data is the same, but if you want, again, to read even random access, you can basically pick one from each disk and then have a better performance. This is instead of like having two headers, I think. Right? Mark?
What?
Yeah. Last session, you remember we talked about two? Yeah. It's kind of like that. Two exactly same disk, but now you have basically two headers that can move independently. Okay? So, but the problem is it doubles the storage requirements. So instead of like 100, like you have still 100 gigabytes of useful, capacity, but you have to pay for 200, right? And also the writing into them is not like improved at all. Even it might be a little bit worse because, for example, if you have like two disks with two different writing speeds, every write is definitely going to take the longer of the two, right? If this disk is a little bit older than this, for example, this also needs to wait for this to finish. So writing is not improved at all. So any question between for the RAID 0 or 1? Right, I guess they're simple. So RAID level 2, it actually uses error correcting codes or ECC and then break a file into bits and spread those bits across multiple disks, right? So what it does is that it basically uses, for example, Hamming code. How many of you do know what a Hamming code is? Just raise your hand. Okay. We have a couple of slides on Hamming code, but I mean the concept is important to know right here, but the details not yet. So Hamming code is instead of like having a complete copy of data to be able to recover, there are other ways to basically recover a fault, right? Sometimes a fault is that you don't lose a whole of data. Maybe you lose bits of it or parts of it. And that's like what the error correction codes are in general. They're not necessarily efficient to send a packet twice. But instead, as you send the packet, you also, add some parity bits or error correction codes in it that on the receiver side you can recover. This happens everywhere that you are, like all the, like in the video that you stream from internet, every packet that you send to the, Wi-Fi, whatever. Everything that has to do with transmission or something like this, like storage, you have error correction codes. Now, Hamming code, the idea is that for each 4 bits of information, you add 3 bits of redundancy, which then, will be represented by 7 bits. Now, the idea is that using this method, you will be able to recover if one of the bits of this, 7 bits gets corrupted, like flipped from 0 to 1 or 1 to 0. The problem is, usually when that happens, you don't get to know. If you know what is the bits that has been corrupted, obviously you can flip it back, right? So whatever data, even you don't know usually how many bits have been corrupted, but Hamming code basically takes 3 redundant bits for 4 bits of data and then stores them together. Okay, so now the problem here is it requires 3 extra disks for 4 data disks. So it almost doubles your data storage again, right? So if you have 7 disks, basically the useful information is going to be from disk 0 to 3, and then disk 4, 5, 6 are going to be like parity bits. So again, each file is separated into bits. So out of each 4 bits, 4 of the data bits are going to be written here, 3 parity bits are going to be written on here. Again, next one. It's just going to be striped like that. And what it does is that in case that you have a failure of one disk, it's like for each 4 bits, you have lost 1 bit. right? It's as if, like, if you look at the Hamming code, among these 7 bits of A, then you have lost this bit. Now, with Hamming code, you are able to basically, recover that bit. So, and the good thing here is that any of them, if they fail, you can basically recover using this method. But it's obsolete and rarely used because other rates do it better. It's not that efficient in terms of capacity. It's also not that efficient in terms of even calculating this parity bits. Breaking a file into a bits doesn't make sense. So, it's just like that. And it provides a fault tolerance up to, losing one disk, but it's not really used. And the Hamming code itself has a lot of overhead, especially if you want to do it in software. It's just going to be very inefficient. Because RAIDs, by the way, you can do it either in hardware or software. So it depends where the RAID controller is. Usually, obviously, the RAID controller, if it's implemented in hardware, it's going to be much faster, more efficient, and doesn't take the time of your CPU or operating system, whatever. But technically, you can do them. Some of them don't have much overhead on the operating system. Okay, so now RAID 3. RAID 3 is similar to RAID 2, but instead of striping bits, it's actually byte level striping. Okay, so it basically stripes some bytes on this, then on this, and then on this, and then instead of also Hamming, it uses a parity disk. So instead of like the Hamming code, it only consists of a parity disk, and so what this disk is specifically dedicated for parity only. So all your data will be stored on the other disks, and then you have like one extra disk that basically for all these stripes you calculate one parity block or basically byte, and you write it into this. Again, next set of bytes you calculate a parity, and then on this. And for those if you're not familiar with parity, again, parity is a way of redundancy to be able to tell if something has happened, or some data has been corrupted or not. So the simplest way, we actually have going to see in an example, is that if you have 1 byte, this happens in serial communication as well. If by any chance you do work with COM ports or anything like that in your small projects. So if you have like 8 bits of data, there are like, either 0 and 1. So basically you count the number of ones in them. The number of ones can be either 0, 1, 2, 3, 4, 5, 6, 7, right? Or 8 of them, all of them. So if the number of zeros in these 8 bits are odd, you add 1. If the number of ones in these bits are even, then you add a 0. So by doing this, you ensure that by adding this bit, the total 9 bits always have an even number of bits, which are 1. This is called even parity. Okay? So by doing this, again, the receiver always expects out of each 9 consecutive bits, only evens of them should have 1. So if it counts and then figures out, 1 is like, flipped, or the number is 1, the number is like odd, then okay, something is messed up. Probably one of the bits have flipped. There's no way that they can recover from this because they can't tell which one of them happened. Maybe the parity bit itself was the problem. They don't know. But at least they would know that, okay, there has been a corruption in the data. So one of the method is that, okay, I'm going to request it to send again. So this is the simplest way. And the reason is usually you got to think about your fault rates. So if for a transmission is reliable enough that the chances of 1 bit getting flipped is not very high, then chances of 2 bits getting flipped is you have to multiply those. Like let's say 1 in a million is for 1 bit, then for 2 bits is going to be 1 in 1,000 billion. So it's just like, you're reducing all the possibilities. So then you're just like taking as. But on the other hand, if it's the communication, for example, is faulty, it's noisy, then chances are higher that 1 bit happens. So parity bits just introduces a lot of retransmissions. On the other hand, chances of having 2 bits is not very low. So if you have like 2 bits flipped, then your parity actually doesn't change. So you think the data is okay, but actually it's not. So parity is not enough. Then you have to like do another, scheme of error coding, correction codes. So now let's get back to rate. So rate level 3, again, it just like stores a parity bit. And again, the idea is, on the other hand, disks themselves have some error corrections, right? They don't just happen to corrupt by themselves. So there is a difference between communication and here. Communication always have noise. If I'm sending some, zeros and ones on the air for Wi-Fi, there's always going to be something messed up. Here, on the other hand, that's not the case. So the parity is actually still useful, because what might happen is not corrupting some bits in the middle of this, but it's losing the whole disk. And if I lose the whole disk, I will know which disk has been, gone out, bad, and then I can use the parity bit to actually recover the data that was stored there, right? So that's why, it still is useful. Now, the good thing and bad thing about this one, again, the RAID 3 is also kind of obsolete, because RAID 5 does a better job for this. We're going to see why. And it requires 1 parity disk for, no matter how many disks you have, you add only 1 disk for parity. And it's good for long sequential reads, because if you have long sequential reads, then you want to basically read A1, 2, 3 together. So then you can basically read all at the same time. If you only want to read 1 sector at a time, then you have to basically check that disk one at a time, the other one. And also the reason is because these disks in RAID 3, they are synchronized, meaning the head reader of all of disks are moving at the same time. They all point to a same sector and track at the same time. Now, why? I mean, that was how the RAID 3 was, but this ensures that the disks are synchronized, and this is byte level stripping, right? So as you're just writing a sector logically, these move at the same time and write at the same time in the same location. And again, for reading is also the same. So when you want to read A1, 2, 3 together, basically your heads are always moving at the same time and reading together. They basically read 1 byte, and then you get 3 bytes in this example. But if you want to have random access, because of the synchronous head, that's just not going to happen. If you want to read A1 and then B2, you can't do that in parallel, because once you are reading A1, this disk is pointing at A2, whether you want it or not. Okay? So then if you want a B2, you have to wait, and then this will be pointing to B1, which again you might not want. So this is one of the downsides for RAID 3. Okay? And also, again, you have to write to the parity disk. So if this disk is, a little bit slow or old, then all of your disk writes will be slowed down all the way to the performance of this disk. Okay? Any question? All right. So next was going to be RAID 4, which is similar to RAID 3, but it employs, instead of byte striping, it uses block level striping. And it stripes the data in much larger blocks of data. And so instead of, again, separating each byte, it's going to use blocks, right? And read performance is improved as different blocks can access simultaneously. This one, instead of having synchronized heads, they work independently. So you take this block, you take this block, you take this block. If you are reading or writing sequentially, sure, it's going to be the same. If you are not, you are reading blocks at a time, and then because of that, now you have independent blocks. So A1, C2, B3, they can all happen at the same time. Again, that's usually the best scenario. If you want A1 and B1 and D1, obviously you have to the bottleneck will be this disk, right? And it still suffers from the bottleneck. Again, the disk, you have a dedicated parity disk, which is this one, and it's not going to be as good as RAID 5. So RAID 5 is going to be a kind of improved version of these two. Okay? Any question on the RAID 4? Yes. It's fine. Any single disk that fails, you can recover it by calculating the parity again. So that's with the that's one of the actually interesting thing about parity, that although it's considered as parity, but when you calculating or correcting or whatever, it just doesn't matter. It's one other data. So you can consider that now this is the parity of these three, or this is the parity of these three. That's not always the case with error correction codes, but for parity it's always the case. Because usually, for example, we're going to talk about parity is basically XORing different bits, right? And when you have like XORing zeros and ones, it doesn't matter which one is the parity or which one is data. You just keep doing that. But if you want to read data, well, this is the data. This is not your data, right? This is a somewhat flipped version of this. But this is your data. So as long as you don't have any corruption, these are your data. If in the case of a corruption, you can easily just calculate the parities again, and that will be the recovered data. Okay, so RAID 5 is basically similar to RAID 4, but instead of using a dedicated parity disk, it stripes the parity themselves. So that's why it's called the striping with parity. So the parity itself is also striped, right? So you can see here A1, A2, and A3 on here. The parity is stored here. For B, B1, B2, and B3 are here. The parity is stored here. The C parity is here. D parity is here. So what are the benefits for this? So one is that it's just that you don't rely on one disk for parity, so you don't stress that disk a lot. So the problem, for example, in this case, let's go back, is that now let's say you have this. If you want to change A1, something in A1 you want to change, obviously the parity bits of A, all of them together, also changes. So once you want to modify this, you also need to modify this. If you want to modify this, you also need to modify this. If you want to modify this, you also need to modify this. Any change, this has to work. So that's why it basically puts a lot of a stress on this disk. That's why it's like a bottleneck. So because usually you're assuming that writing is or modifying is uniform. So basically your data is basically divided into these disks, and you use them evenly. But then every modification you also need to use this one. Okay. But in terms of but in RAID 5, you're evenly, spreading these out, and then now you don't have to do that. Basically, you will use up all of them together. Okay. But relatively, this is similar to RAID 4. But this is used a lot. RAID 5, and the reason is you add only one disk to your disks. So let's say in this case you have 3 disks. And now you add another disk, but it gives you, first of all, in this matter, you give redundancy and performance, both of them. And any failure of any single disk will be recovered, easily. So now the issue is we're not, digging in detail, but you usually yes. What do you mean you only have?
Like here you have 4 disks. So you have data in disk 1, 2, and 3, and then you have another disk that has
okay.
Parity. So what if you had, instead of 3 data partitions, you have 1? Then wouldn't you have redundancy in 2 other disks?
I'm still not getting the question. Maybe I didn't cover it well. See, first of all, we're not dealing with partitions here anymore. Partition is something logical. We are striping the blocks. So your data is going to be stored in blocks into disks, right? Now, what this does is that out of each 4 blocks, out of each, let's say 3 in this, out of each 3 blocks, it's going to calculate one parity block, and it's going to stripe them like that. Now, you cannot say that I don't have A2. Okay, maybe you have a small file that only uses 1 block out of 4, which then you update only this. But these are like a bundle. So next time, if you want also a small file, which also is like in one block, then you're going to use this A2, right? And once you use A2, then this bundle is going to recalculate its parity, and that's going to be AP, right? And yes, again, if you are dealing with single, random, small files, the benefit of parallel is not going to be that much, because if you only want to access A1, yes, you are accessing A1 from disk 0. That's it. But a lot of the times that's not the case. You have a large file which is a lot of blocks. And in this way, you are splitting it into different blocks, and you're just like sending these different blocks to different disks. And now, both for writing that, it just like speeds up, because now you're writing 3 blocks of that file at a time. And also for reading. Again, if you want to read a large file, you want to read block at a time. But then if you want to read all the blocks at a time, then this way you're reading using 3 disks.
So if one of the data is lost, then how would you know where the parity?
Okay, that's a bit of a scheme. So the easiest, like in this example, the easiest is you calculate the division by 4, for example, and out of each set of 4 blocks, so in this case, always A is here, B is here, C is here, D is here. Again, next one, E is going to be here, F is going to be here, G is here, E. That's like a simple. But that's like what the rate controller does. You don't have to worry about that. Again, just based on the block number, you can tell which bundle it is in, and based on which bundle it is in, you can tell, which one has the parity bit. And again, in this case, it doesn't matter. Whatever disk failed, you calculate the parities of the other disk, and that will result in the data which should be in here. So, and usually again the rates are for reliability. So a lot of the cases there are data centers that use a lot of these, and the numbers are just like add up, right? So you have only one hard disk, and chances of losing your hard disk is something like the expected length of the age of the hard disk is like, let's say 5 years. But now think of a data center like for Facebook or Google, whatever. They have like millions, right? So they just like popping just like that. The hard disks are just like failing like that, right? So that's why they need so much redundancy, even like center like a small data center, right? Now losing disk again is something. It's one chance. There's always a service time, which is the expected life of a disk. There's also a repair time, which takes. So if you lose this, then you replace it with a new disk. Now, again, the rate controller needs to calculate all of these blocks parities and then store it on that. This is also a repair time, right? Now, during that repair time, your data is not safe anymore. If you lose this disk, okay, you're fine. At this moment, you have these data on the other ones. They're retrievable. But in order to get this back, first of all, there's some physical movement that you need to do. You have to replace this disk, for example. Or if you have like some available disk somewhere, that doesn't happen anyways, you have to still read all of them and calculate the parity and then write all of this. Now let's say this takes 2 hours. During these 2 hours, you don't have data anymore. So if you happen to lose this disk, then you actually lose data. Okay? So again, this might not happen at home. That's why a lot of people actually use RAID 5, and it's fine. But when this happens, and again, these hard disks are also servicing requests. They're not just there to, probably fix this. If they are, then they won't be usable. All of these data won't be accessible during that 2 hours. So maybe even losing one disk is not that safe after all. So, let's just go over this. We already covered that they actually evenly wear out, and they have the single disk failure. They can recover it, and we're going to cover this in a second. Any of these problems, if you want to again modify one disk, we're going to go over that. So in RAID 6, you actually make it even one step further. So the parity bits are not there anymore. You use other error correction codes. So for example, one popular one is Reed-Solomon code, which is complex. We're not going to like dig into it, but it does a little something with the pattern and gives you, instead of like one parity, it's just like 2 blocks. So that's why it needs like at least 4 disks. So out of 2 blocks, then you have like 2 parity bits. But what it does is that it now is basically having 2 parity bits. Let's say for A1, 2, and 3, you have AP and AQ. For B1, 2, and 3, you have BP and BQ, and so on. Now, what this is gonna like waste more space, obviously, because out of these disks now you're using 2 disks, which are not giving you a space, but just like redundancy. But they are able to basically recover from any concurrent 2 concurrent disk failures. So, right now, if you just lose these 2, you still won't lose any data. Using these Reed-Solomon error correction codes and whatever that you've stored on this, you still can recover your data. Any of the 2 disks, it doesn't matter, you still can do that. Okay? So the specification of RAID 6 doesn't actually specify Reed-Solomon, but this is like just common. Now, what I went, like both, let's say in RAID 5 or 6, what happens if you want to basically modify a sector? What needs to be done? So, in order for this to be done, let's say you want to modify, this is important because this is happening all the time in any of these. So if I want to modify this B2, first of all, the whole bundle of B1 to B3 and BP should be read simultaneously. Then, B2 and BP will be, basically B2 will be subtracted from BP. Right now we know that BP, which is the parity, is a combination parity for B3, B2 and B1. Okay? So, you read all of them together, you subtract B2 from BP, meaning you do the parity again and say, okay, what if B2 is not there anymore? So BP, what would BP look like if it was only for B1 and B3? Then you modify B2, and then you have to calculate the parity again, just to see, okay, the parity was for B1 and B3. Now I have a new block of data. I calculate the parity again. Oops. That was my bad. Alright? And then you have to write it. So even a single sector modification involves a lot of steps. That's just like what it's write amplification. So especially for writing, you have to do a lot of, modifications. For reading, it's simpler. You just read. Okay. Any question on RAID 0 to 6? We're almost done with basically all the levels of RAID. Now, we have nested ones. So RAID 0.1 or RAID 0 plus 1 is a combination of RAID, which basically gives you the both benefits of 0 and 1. How is that? You basically have 2 disks which are RAID 0 together, and another 2 disks that are RAID 0 together, and you just mirror these together. So now, anything that you want to read A1 and A2, you're reading at the same time, which was like, RAID 0, but the problem was with RAID 0 was that it didn't give you any redundancy. Well, here we are. We add another redundancy, just like a full mirror. Right? So this is obviously gonna like waste the space just like as RAID 1, because you're mirroring your data completely, but the performance is going to be like RAID 0. RAID 0 has the best performance because it's just like in parallel doing 2 at a time, and with no parity, nothing, just like much faster. So the other one, which is even more popular than this, is RAID 10. You might have heard. RAID 10 is actually not a RAID level, but it's just like RAID 1 and 0. So it's the reverse order of that. You just like do RAID 1 together, so you mirror these 2 together, and then mirror these 2 together, and now you implement a RAID 0 on top of them. So whatever the data you have, you split it, and then you mirror it on 2. You split it, and then you mirror separately. Right? And even though in theory they actually look very much the same, but I guess like for some reason this is better than the 0.1. So that's why you might have heard like RAID 10, RAID 10. It gives you better performance and reliability. Alright? So, these are other nested ones. 0, 3, 50, 60, 100 even, like RAID 1 and a 0 on top. So, 2-level parallelism, and then mirroring at the bottom. So, okay, so this is an example of parity bits. You have like one block, you have the second block, you just like XOR all the bits together and get the your parity block. 0, 1, and 0 will be 1. 0, 0, 1 is 1. 1, 1, 1 is 1, right? XORing 1 and 1 is 0, 0 and 0 is 0, just like that. And again, the good thing about parity is that any of these that you lose, it's going to be exactly the parity of the other ones. So it doesn't matter which one was your parity, you can always reconstruct it. Okay? Hamming code examples are here. This is not, you don't have to actually be able to calculate it a lot, but it's just like simple to know. Parity bits, you actually assign 7 bits, 4 bits of data, 3 bits of parity. Each parity bit is calculated based on some of the other data bits. So what you do is you calculate a parity when you receive it, and then if it's 0, it seems fine. If it's 1, then either P1 itself or D1 or D2 or D4, one of them was flipped, because P1 is supposed to have a even parity for these 3. So if you calculated these 4, they should always end up 0. This also should be 0. This also should be 0. So when you want to recover this is an example. So you get the data, you calculate P1 and P2. If P1 and P2, any of these P1 or P2 or P3, if they are 1, then there is a problem. Now where is the problem? If P1 is 1 and P2 also is 1, then the flipped parity bit is D1. If P1 and P3 are the problem, you can take either this or this, but it also will reflect in P2. So if P1 and P3 are 1 and P2 is not 1, the problem is D2. If P2 and P3 are 1 but not P1, then the problem is D3. If all of them are 1, then the problem is in D4. So this way you can basically recover which was the parity, or which one was the bit that was like flipped from 0 to 1 or from 1 to 0. Okay? So we're going to cover I/O systems, I guess, for our next session. We have a few slides. It's an intro, but it's worthwhile. All right? So see you on Thursday. Mm-hmm.
At this point, should we be able to do like 1 or 4?
What?